Okay, I think perhaps we can start now. I have the pleasure to be chairman for this session, and we have 4 presentations before lunch. And we start with the first one is by Professor Ballauff, and it's about proteins interactions with polyelectrolytes. And this is a little bit continuation of my presentation because I didn't come so long as you. Okay?
Okay. Yeah, thanks. First of all, of course, I would like to thank the chairman, Björn Lars, for inviting me. This is the first time I'm in Singapore, and I'm enjoying very much this very interesting conference. I learn a lot, and I look forward to, of course, listening to the other talks. What I'd like to present today is a close collaboration with my colleague Giorgio Biella, who is a theorist. What I'm going to present here today is a one-to-one mixture of experiments and theory. So my student Shidian did the calorimetric experiments, and Xiaoshu did the simulations helped by others. And we got a lot of inspiration, and we got the materials from Rainer Haag, who has a sort of a biomedical program at the Free University in Berlin. Now the question we had a couple of years ago, so of course, is a very clear and very central problem in medical techniques. So if you have an a surface in some device for medical purposes, you very easily get absorption of proteins, and of course, if the proteins are absorbed, they mostly degrade. And then of course, you use some polymer layers, and but this is a very difficult problem because you have approximately 1,000 proteins you have to consider interacting with some polymers. You always have charges present, or there is no uncharged system in this business. And of course, we have only very vague ideas about the general driving forces. So we came to this by putting up this review, which turned out to be very lengthy and tedious and not very insightful because we lack the basic understanding. So now we then set the goal, we have to understand in more details the interaction of proteins with polymers and of course with polyelectrolytes. So this is the first task we had. And then this is the main point. We have to be able to combine this with computer simulations. I mentioned so it's 1,000 proteins, and you can maybe work with 10 of these proteins in the lab. The other ones are very difficult to get, and the question is, how can the computer help us not only to understand things, but then to solve practical problems? This is, I'm trying to convince you that the combination of experiments and simulation is very useful in this regard. So this is, of course, well known. Proteins are polyanthalides. They have a surface distribution of charge which is not even. So you have, for instance, this blue patch of positive charge. And of course, this is a very classical thing. And I should name people like Gerald Manning, Timothy Lohmann. So you have a net charge, of course. The counter ions are very important. And very often the biochemists talk about unspecific interaction, which is not quite correct. These electrostatic interactions can be very specific, and I think this is a very important point. Now, there is one thing which is, I believe, central to all this business. If you talk about interaction of proteins and polyelectrolytes, this is counter-ion release. So we make a very simple Gedanken experiment. We have take this blue patch of positive charge. Then we take a polyacrylic acid or some negatively charged linear polyelectrolyte with the condensed counter ions, and we mix it. And then it's evident that this polyelectrolyte can be hooked on. So the patch becomes a multivalent ion, counter ion for this polyelectrolyte, and a part of these counter ions are released. So you gain a lot of entropy in your system by releasing this counter ion. So it's a strong driving force for formation of the complex. And if this is related to the translational entropy of the counter ions, of course, the this should scale with a logarithm of salt concentration. So that's a very strong force, and indeed this is the main driving force, as I will show in a minute. Now, this is not a new idea. I must say we learned a lot by reading very old papers by these gentlemen named Thomas Record, Timothy Lohmann, and others, and they wrote a nice review and looked into all the details for these biological systems. But of course, they mainly did work on RNA interacting with some very complicated repair proteins and things on. This is, of course, a very difficult thing. But I think the concept of counter-ion release is rather well established in biochemistry. But there is a second, more subtle point. So if you look into the binding constant in biological system, you have, for instance, DNA in a repair protein, then you see that the free enthalpy of binding has hardly any temperature dependence. So you have to look at this axis scale. So it's a very small and very peculiar shape. So it's not the classical Van 't Hoff kind of dependence. So you have a highly nonlinear relation. And this is, of course, well known. And this is related directly to this very strong enthalpy cancellation. So if you look into the systems, and this is, of course, known for many systems in colloid science, for micelles and so on, you have this very strong enthalpy cancellation. And we were now interested in, can we understand the relation between counter-ion release, a driving force, and this kind of phenomena a little bit better using well-defined model systems. And this is what I'm going to show in the next slides. So the question is really, we have hydration force, we have electrostatic interaction, and can we understand the general thermodynamics? And of course, the question is already, does electrostatics matter under physiological conditions at high salt concentration? And the question is yes, indeed, it does. And counter-ion release force is very much operative, even under these conditions. And of course, the question behind all this is drug design. You know, can we use a computer to design, for instance, polyelectrolyte as drugs? We started out by looking into HSA, which is, of course, the most abundant and the most studied protein. You have these different sites. In many respects, HSA, human serum albumin, is sort of the garbage worker of your body. And so we looked into the interaction of this HSA with short chains of polyacrylic acid at approximately at pH 7. So we took a very short chain with 25 units only. So if you take long polyelectrolyte chains and mix it with proteins, then you are in a field called complex coacervates. And you find approximately 10,000 papers. You don't want to read all these papers. The first one dates back to 1911. But because it's very complicated, you have all kinds of equilibria. I will show in a minute that you have here a very simple problem. Indeed, one polyacrylic short chain polyelectrolyte is bound to this one, and you can do, of course, a simulation on this. Now, my co-worker Xiu did isothermal titration calorimetry. This technique, I guess, is well known to many of you. So you mix, for instance, you have the protein is already in the sample cell, and then you add the polyelectrolyte. And then, of course, you have to do lots of experiments because you have, in essence, two variables. First of all, you have the salt concentration. If you talk about a logarithmic dependence on salt concentration, you should change the salt concentration over a wide range, of course. And then, of course, you have to go between room temperature and 37 degrees and check this. And then, of course, you have to be look into the conditions of buffers and so on and so forth. So then you get typically these curves. You put in a little piece or droplet of your solution. You have this heat signal, but of course the dilution, these are these blue signals. The dilution, heat of dilution is very strong too. And we found out, and it took us quite some time, that to really come up with this data. So you have to push this technique to the brim. And I should mention, of course, Pierre Scharf in Strasbourg, who did this experiment some 20 years ago. I think he was the first pioneer on this. So it's a difficult experiment, but it's doable. Okay, then we have now the binding constant. And then my colleague Joe and his student Shao came in. So we had this model, and we said, well, can we model this? This yellow thing is the short polyelectrolyte. So it's a coarse-grained computer simulation. And the specific thing here is now it's implicit water and explicit ions. So the water is treated as a continuum with a certain dielectric constant, but the counter ions are treated explicitly. Now I have this movie, and here you see this was a surprise for us. So if you're a little bit familiar with the HSA, then you know this is the so-called pseudo-2 site. So this, as I said, HSA sort of the, maybe I run once more, the molecular garbage worker in your body, and it's meant to grab sort of short misfolded proteins, and the polyelectrolyte is going to this side. And if you think about this matter and check the literature, then it makes good sense. We don't have a direct proof for this, but it makes good sense. But then we looked into the simulated and the measured equilibrium constant, and we found surprisingly a very good agreement. So we had, when we started this work, we had said the computer gets the sign and the order of magnitude, nothing more. After all, it's an implicit water simulation. So let me go very briefly into the details. So we have a steered Langevin dynamic simulation. So you look into, you go to a certain distance of the centers of gravity, you add up all the forces, and then you shift it a little bit nearer. Again, you add up all these averaged forces, and then you get a potential of a mean force, and the minimum of this is delta G. This is very cute. And then, of course, we have in the experiment, you map it on a Langmuir model, and then you have to look into the details. So the Langmuir model is not so trivial as you think. So you have to look into the binding volume. There must be finite binding volume, and then you can compare it. Here you have the theoretical value and the experimental value. This looked very good. We said, gee, this is nice. Maybe this is a more general thing. And then Joe came up with some, as a good series, here they have series, and physicists have always toy models. So this is a protein. It's always, of course, everything in theoretical physics starts out as a sphere. And so you can, then you have this patch, and then the polyelectrolyte is interacting with the patch. And then you can look into all the details, and you can convince yourself that this counter-ion release is a very robust thing. So whenever this polyelectrolyte, this linear polyelectrolyte is interacting with the patch, you release a couple of counter-ions. In the case of polyagrylic acid and HSA, there was 3 counter-ions which were released. And this scales with the logarithm of the salt concentration. And this is a robust phenomenon. Now we got a little bit more daring, and together with Rainer Haag et al., we looked into these hyperbranched or dendritic polyglycerols, and we had already dendrimers here, and I believe we have more lectures on dendrimers. So we have this typical dendritic, highly charged structure. And then Rainer Haag and his co-workers came up that you can block inflammation. So you can, in essence, use this hyperbranched polyglycerol as a drug. And the idea they got some time ago was that if you have this inflammation in all these pathways, L-selectin, a very special protein, is blocked by this dendrimer. So the dendrimer is working as a drug, and then you suppress this inflammation. So it was interesting to have different proteins interacting with this object. So we first, of course, had the task to study the dendrimer in more detail, which is, of course, this is a well-studied class of polymers, but we did again a study. And then we took, of course, a very clean and robust protein, namely lysozyme, which is positively charged. So this thing has an overall negative charge. This is positively charged. And then we take HSA again. So HSA is a very important protein because it's the most abundant protein in your blood. So if you construct a carrier and drug delivery, whatever, you should first be worried, what is your carrier doing with HSA? If it's going to do terrible things, it's not a drug. And so it's good to study this. And here you see it's a negative charge too. And normally you would expect that these two objects should repel each other, which they don't do. I have a movie. Sorry, it's a little bit hectic. Hopla. Once back. I hope it will run. So Joe first studied the dendrimer, and you have these counter ions. What you cannot see for this movie that you have a rather dense layer of condensed counter ions, and then you have, of course, these free counter ions, and then in the simulation, this coarse-grained simulation, you can look into all the details. What is approximately the surface? It's a nearly spherical object. Where are the counter ions? And then the effective radius we set to a point where the potential falls off as the Debye-Hückel form. So it's an arguable thing, but if you do this, and this is of course open to discussion, and I should add that Joe Gibella and his student Rohit are doing now explicit water simulations on this, and the first results show very nice agreement with this coarse-grained simulation. So I think we understand the dendrimer quite well.
Sorry, I need to understand it. So the ion potentials are just primitive model potentials with dielectric constant, right?
Yeah, right. So it's implicit water, so you have a dielectric constant of 80 or something in the continuum. And then we compared the simulations with data from dynamic light scattering and from the theta sizer. So the theta potential, and then you see the surface potential and of course the effective surface charge levels off. This is of course what you expect for such a system. And then I think very important, if you talk about counter ion release, you know that you have the spherical core of your dendritic structure, and then you have a shell of condensed or confined counter ions. Now you can put a number on this concentration, and then you see 2-point-something molar concentration. This is far more than 150 millimole in your bloodstream. This means counter ion release is operative under physiological conditions, and you can calculate the gain on free enthalpy if you release counter ions. So this is the number of released counter ions, and you have to multiply this by this sort of van 't Hoff term. This is the concentration inside the shell, and this is outside. And if you do this, later on, you get approximately 80% of the delta G you measure in the experiment. So you can do calculations with these polyelectrolytes with these very simple sort of freshman chemistry type expressions. So, and then we, of course, did the IDC experiment. We had, first of all, you start titrating the polyelectrolyte into the protein and vice versa. And you convince yourself that you do everything right. And then you see for this dendrimer of second generation, it's approximately a 1-to-1 complex. And again, you find this relation, this linear relation between the delta G, what you measure with salt concentration. And this is, I think, very general. We not only saw it in the simulations, we also saw it in all experimental systems we studied so far. Here, these yellow points are simulations, and they kind of rather near to the points. I come to this in a minute. And what you see here, if you go into these details, you see that at 150 millimolar, this G2 is hardly interacting with HSA. So if you are worried about using HSA or this dendrimer as a drug, you can at least be sure that it does not interact under physiological conditions with HSA, and you see only if the salt concentration is small, it does interact. And then I think you do another very important experiment, should be done for all nanocarriers. You look into the CD spectroscopies of the HSA and HSA with the complex, and you do this at different temperatures. And for many dendrimers, and this is of course a lot of literature, you see that in particular that the dendrimer adsorbed to HSA is strongly destabilizing the dendrimer, and it's certainly not a drug. So it's a very simple experiment, and whenever you have a new drug, do this first before you administer your new drug to these innocent rats or whatever you have. Maybe if this sort of test is not positive, you should not get it to the rats. Okay, then of course the simulation tells us again that this G4, or this is a snapshot of the simulation, goes again to the pseudo 2 side, and if you look into the details, the dendrimer is even a little bit distorted. So it's not strictly the spherical surface here anymore, but I think for such a coarse-grained model, it may be not good enough. And again, we looked into this potential for mean force, so the maximum is delta G, and here we had these blue points are the experimental data from IDC for G2 interacting with the HSA, and then you see these simulated points. And here at a little bit higher temperatures, you have, of course, not full agreement, but here the agreement is really good. And I think you find two more important points. First of all, you sort of mimic very well the measured constant. And the second time, the temperature dependence, look at the scale here, is very small. That's nice. But then if you look into the enthalpies you measure from your experiment, then you see a huge difference. So it starts out at a low temperature, it's strongly negative and becomes strongly positive. So it's a huge and very strong dependence seen in many systems, I should say, which are governed by hydration. So you again show you the delta G. The same thing is for a complicated protein factor interacting with RMNA from this biochemical group. And so if you then, of course, use this equation, so maybe I go back, the normal Fantoff equation, which stops right here, would not give a correct description. All these systems are, of course, characterized by strong specific heat. And if you do this, you can calculate delta H and delta S. And you see, like in the typical biochemical systems, this strong enthalpy cancellation. By the way, just one technical remark here. This is the red points are the enthalpy, the true binding enthalpy you derive from this kind of evaluation. The other red points are the directly measured enthalpies, and they don't agree. And I should say there is no reasons why they should agree. So there's a lot of, and we made this mistake ourselves, that to take the measured enthalpy as the enthalpy of binding, which is wrong. And I could go into the details. So we see something which is, of course, very similar to what biochemists see. But now we can say, here you see the simulation. In this kind of y-axis, you see practically full agreement of the measured and the simulated free enthalpy of binding. And again, you see that the entropy cancellation must be total in this case. Now we wanted to look into this selecting problem, and we used lysozyme as a model protein. Then you do the IDC experiment, which is very easy. So the point of inflection gives you directly the number of bound lysozyme molecules, and you can do the same thermodynamic analysis, and then you make a simulation, and you can watch the lysozymes being hooked on to the surface of the dendrimer, and you can, of course, now look into the details of your IDC experiment, because what you see here, and if you analyze the details, you see it quantitatively, is the negative cooperativity. So in all these IDC models, the delta G is a constant for all ligands binding to the central dendrimer. This is not the case. It's not true. So you have this negative cooperativity, and you can model directly your IDC data and get a much better understanding. And of course, you have then you do the same, the potential of the mean force. You can calculate the number of released counterions from your computer experiment, which is very nice. And then you can put it into the Van 't Hoff equation and convince yourself that a counterion release is the main point. And then you do the same thing for the L-selectin, and you see it's a rather strong binding as expected from the earlier experiments from the Haag group. And then you can, of course, go to the experiments. So this is L-selectin interacting at 150 millimolar with these DPGS, the charged dendrimer. You compare this to the simulation, and you find the binding affinity here, something like 15, here something like 16 kBT. So this is a good agreement. And of course, these selectins are very difficult to get and to experiment with. And so it's nice that we can do the thing in the computer, not doing complicated experiments. And then we knew from earlier work that another selectin, the so-called E-selectin, does not interact with the dendrimer. And indeed, this is exactly what the simulation shows very nicely. So this means, at least for this highly charged system, I should be clear on this, it looks like the computer is a good tool for prediction of these interactions. So this is the punchline. We have been measuring and simulating these binding affinities of highly charged polyelectrolytes with proteins, and now we are convinced that the counterion release is approximately 50 to 90% of the story. We have been able to nearby quantitatively model these enthalpies, and so it's very good prediction of the binding constant. And again, as I said, if these electrostatic factors give you approximately 100% of the binding enthalpy, you necessarily are forced to the conclusion that in these particular cases, I should boil it down to these cases, the contribution of the water, of our hydration, which you see in the strong enthalpy and entropy contributions, are 100%. So EEC is 100% in these cases, and we hope we can continue to see how general this conclusion is. So I already mentioned Shidiran and Xiaoxu and other people. And of course, my colleague Jubela, who unfortunately got a very good position in the University of Freiburg. He will leave our institute. We got money from these institutions, and I thank you for your kind attention.
Thank you very much for a very interesting talk, and now it's open for discussion. Yes, please.
Yeah, sorry. Two questions, I guess. Did you do any experiments and any simulations in the presence of divalent counterions, magnesium, which you would also have under physiological condition? And second question, the simulations were always done with one, like dendrimer, for example.
One dendrimer, yeah.
And one polyacrylic acid or whatever it was.
No, we have one dendrimer, and you offer a couple of
proteins, yeah.
proteins, yeah.
But in the other case, it was one polyelectrolyte and several proteins.
We tried several
because I was
polyelectrolytes.
wondering whether for a negatively charged polyelectrolyte, and you have if the net charge of the protein is positive in principle. No.
It's in case of HSA, it's always negative.
Oh, it's always saying.
It's
okay.
always absorption on the wrong side. Yeah.
Yeah, and okay, so you only okay. That answers this question. So first question.
First question. Yeah, of course. You name a very important problem. This is exactly what I suggested to my theory colleagues. Add a small amount, maybe hopefully some the order of physiological concentrations of a divalent ion, and see what happens. We didn't do this. But of course, it's very easy doable.
Yes. Yes, please.
I was in the same direction. It means the albumin carries half of our blood calcium. And this is very much pH dependent. So what is it? The release of the cations when you change the pH in your system. You mentioned in the beginning it's very much pH dependent.
No, we have of course used the physiological pH, but we of course this is of course all this is on the list of things we should be doing.
Things to be done, yeah.
And so believe me, I'm pushing my colleagues from the computers department. Unfortunately, one colleague got lost, but I tried to grab him and just doing this experiment. In particular, these divalent ions, of course, calcium, and of course, one should be worried about ion-specific effects too. Yeah. And Joe worked on this, so there's a lot of lists on the agenda.
And just a remark, with your L and E-selectin, you are on the inflammatory side. It's very important what you have shown. Very nice. That one is not interacting. Yep. The other one, that's the most important thing in inflammation as first reaction.
Yeah, right.
So
yeah.
very excellent, really.
Thank you.
Yes, it's actually a lot of questions here. So I know, I think you were the first, please. Yes. No, please. Yeah, yes.
Okay, I have a question. Oh, very good work. You mentioned that there has been any notable denaturation for the protein and for also anions.
Yeah.
And if you think about some globular and stable structure of the proteins and the other counterparts, then it's hard to think about that all of the ionizable groups of both sides has been reacted.
No, not all. No.
Not okay. So how could you make a simulation taking account of the portion of the ionized groups, or which has finished the reaction?
So what you do is, of course, at a given pH and a given monovalent ions at the moment, you approach the protein to the dendrimer, and you see, of course, this potential of the mean force, and then you see at the minimum of these positions the number of released counter ions. So you can read it off here. It's in this case maybe 3. So among the many counter ions, only 3 are released, and this is already enough.
How could you count experimentally the number of the released ions?
Yeah, this experimentally you plot, as I showed, you plot the ln of the binding constant. So you plot delta G versus the logarithm of the salt concentration, and then you can convince yourself that the slope is a number of released counter ions. This has been shown by the biochemistry people like Reckitt and Lohmann. So you can see, get this number of released counter ions from experiments and from simulation and it agrees.
Yeah, it's maybe true if the delta G is mainly coming from the reaction, coming from the release of the counter ion. But there should be another interaction, for example, hydrophobic interaction, hydrogen bonding, especially hydrophobic industry has opposite,
Right.
exothermal reactions. Therefore, they may have a cancellation between them.
It's cancellation. This is exactly what we conclude, that we have this huge enthalpy and huge opposite entropy contributions then cancel off. And a very important point, if you denature the protein, then you get an additional heat. And this, of course, heat is just related to denaturation. It has nothing to do with binding. So therefore, we took great care with the CD spectroscopy to make sure that the HSA and the other proteins are not degraded or denatured.
Okay, I think you also had
So the counterions of the polyelectrolyte are treated explicitly, but there's another similar contribution of the protonation, deprotonation equilibrium at the protein surface, which is not included in the simulation, I think.
Yeah.
And to me, this seems like an important approximation. I mean, important missing factor. Can you comment
Well,
on
if
that?
you look into the for Zutlo-2 side, you have lysins. So in essence, you have fully dissociation. So you don't have you don't do a weak polyectrolyte. So you have a strong polyectrolyte, and so
I'm talking about protein specifically.
yeah, but this is I have HSA, and then you know from the simulation, and the literature convinces you that, for instance, linear, this is the most simplistic case, the linear polyectrolyte goes into the Zutlo-2 side, and you know exactly, and we have it from the simulation, and even now from this explicit water simulation, you know with what amino acid this polyectrolyte is interacting, and then you don't see any problem. But of course, it's an important point, and one could look into this. But here it seemed to work quite well.
Thank you.
Thank you.
Then the last question.
Okay. Very nice. I'll make it short. You have said that normally entropy wins. Did you yet find any case where you have a enthalpic contribution to the binding?
Well, yes. In these cases, of course, you have huge positive and negative, and you have this cancellation for these strong polyectrolyte cases. So I should make it very clear. So if you have uncharged polymers, then of course different things may occur. But it looks whenever counterion release is a major driving force, then indeed it's the entropy of these released counterions and maybe some electrostatic interaction.
Yeah, because we found one case where we have a change of the water content of the complex. And then actually we also have another driving force for that direction.
And my colleague Judy Bella, as series, is far more cautious in making these statements. He said, well, you have to be very careful. And so I boil it down now to strongly charged polyectrolytes and nothing more.
Yeah, and one more short, in the beginning you mentioned MOPS as a buffer.
Yeah.
Is there a strong influence of the buffer on what you're getting?
No, very good point. We have use these MOPS buffer and polyphosphate buffer, and we don't see
thank you.
differences.
Thank you very much for the questions, and now we need to go to the next, but we thank for